Good afternoon, everybody. I'm Pano Santos, and what we are going to do, Haitao and I, is going to present a work that we did for former HP Consulting and Integration Group. Basically, what I am going to present is an overview of workforce planning at professional service companies, and I will also describe a manual spreadsheet approach that the co-author of the paper that you will have available related to this work developed to do the workforce planning in HP Consulting and Integration. That work motivated the optimization models that Dr. Lee is going to present. So he will present a couple of formulations and solution approaches. And also, Haitao will present business impact and managerial insights. At the end of this presentation, I will be discussing lessons learned and best practices in deploying and developing optimization applications. So let me give a little bit of background about workforce planning in professional service companies. People is the most important asset for professional service, and at the same time, labor represents the highest expense in this industry. Workforce resource supply and demand matching is challenging because you need to consider thousands of employees with thousands of skills to optimally match thousands of service jobs. Currently, most of the professional service company use manual methods, and this cannot be sustained if these companies want to optimize workforce utilization and their financial growth. So just let me briefly explain a little bit how the workforce planning process works. So essentially, the main job of a workforce planner is to identify early demand signals. Typically, these early demand signals for the services come in the form of a forecast of a service offering. Then what the planner needs to do is to translate that forecast for revenue in that offering in terms of labor requirements, and then map it, that labor requirement with the labor capacity and capabilities available, and then do gap analysis to try to optimize that matching. Typically, in most service companies, what happens is top executives will take the forecast revenue, let's say for the next 6 months or a year, of each particular service unit, and then allocate budget based on the forecast. And this can generate very serious inefficiencies because there might be certain service offerings where the demand is growing, and then these service offerings will get budget to hire people for that growth. But at the same time, there might be other service offering that the demand is going down, so they won't get enough budget to sustain the people that they have, and they might be laid off. So this really hurts the total cost of the workforce, in the sense that you need to pay the cost of onboarding for the people that you are hiring, and at the same time you are paying severance cost for the people that you are letting go. So this top-down fragmented approach really leads to inefficiencies. And that's part of the problem that we are going to address with our optimization models, try to have a global way of doing workforce planning. So the main objective of workforce planning at professional services is to increase billable utilization of resources, reduce overall labor costs, and properly match service requirements with labor resources, capabilities, and capacity available. So the fundamental problem of workforce planning is to match labor resources with the right skills for the right job at the right time, at the right location, at the right cost. So if you observe that in a service firm, you might have hundreds of thousands of people with thousands of right skills, with thousands of jobs, and different time periods and costs varying based on regions and location, then you have a huge combinatorial problem that you need to address. So this is where mathematical optimization come into play in a very nice way. So given the complexity of this workforce planning problem, what we decided to do is to use a hierarchical workforce planning approach. So at the strategic level, basically we develop a labor strategy optimization model, and this is the one that we are going to discuss in this presentation. And for this strategic model, for a given forecast of a service offering, what you want to do is to determine the budgets for various labor strategies in order to maximize total gross margins or profit. So one labor strategy can be onshore or offshore. So you might consider Germany. So onshore labor resources will be resources that are located in Germany, for example. And offshore resources can be labor that might come from India, China, or Eastern Europe. Labor mix strategy basically is the different type of workforce that you can have: internal workforce, contingent workforce, or agency labor. So basically you contract another company to do the work and they provide the labor. Labor transformation strategy basically entail training and reskilling, hiring and layoffs, and promotion and demotion of your labor. So at the tactical level, basically you will have budgets for all these labor strategy, and salespeople will start trying to fill their quota based on the forecast revenue that they have for the particular service offering. So they will start generating what is called project opportunities. So now the question is, which projects should you select and when do you perform those or deliver those projects in order to optimize the trade-offs among several business objectives while considering budgets, labor resources, and other business constraints. So basically, the output of this particular model will be a portfolio of projects that you want to pursue, and you will know when each of the jobs in that project portfolio will start. And also you will know the labor requirements to perform the jobs of the projects. So basically the output of this model is really a forecast of labor requirements. So at the operational level, what you want to do is to fill that forecast of labor requirement with actual people that optimize the matching between the job requirements and the resource capabilities and availability. And then at the execution level, basically your plans, due to uncertainty of the demand and supply, will become obsolete. You really need to do replanning. So you need to do to have tools that allows you to quickly do the replanning to adapt to the changing conditions that you have due to uncertainty of supply and demand. So let me briefly describe the main components of labor strategy. I already discussed several of the challenges of strategic workforce planning, so I'm going to skip this slide. So there are four main components that you need to consider when you are developing labor strategy. One is capacity, and capacity basically is the amount of manpower measured in FTE. FTE, for example, means that if you have one FTE to perform a job, this means that a person will be allocated to do this job 100% of the time. If you have 0.5 FTE for a job, this means that a person will be working on this job 50% of her or his time. Then you have capability. This represents the capabilities, skills, roles of each individual. So you need to match these capability requirements in the jobs with the capabilities available for each of the resources that you have. Then you have also location, onshore and offshore, as I explained. And then you have workforce flexibility, which means that you have different type of workforce, like internal, external, and also you can transform the workforce by training or reskilling. So these are main 4 components that we are going to model and optimize. In this slide, we try to explain the ideas behind internal workforce and contingent workforce. And the only thing that I am going to say is that contingent workforce is going to be used just to address the volatility that you have on the demand. So you want to hire contingent workforce just to address the peaks of the demand, and you want to permanently hire internal workforce to match the trend of your growing demand, for example. So let me now explain the manual method that one of the co-authors of our paper, Andrei Fusiek, developed. But I need to give a little bit of background about the former HP Consulting and Integration group. So HP C&I offered services all over the world, and there were 4 major regions: North America, EMEA, which is Europe, Middle East, and Africa, Asia Pacific, and Latin America. And basically, the service offering, examples of service offerings in HP C&I were application solutions, integration services, financial services, manufacturing services, etc. The manual approach that Andrei developed was a single period approach where Andrei considered 6 months as a planning horizon as a single period. Then in the manual approach, Andrei considered 4 types of labor: internal workforce, contingent workforce, offshore workforce, and labor agency, and it's called 3PP, third-party partners. And 4 roles and capabilities were considered for each service offering at each region. These were project managers, solution architects, business consultants, and technical consultants. So in this slide, we describe the different parameters in the manual approach that Andrei developed. So I will explain these parameters while I explain the approach that Andrei developed. So consider a service offering at EMEA, for example, financial services. And suppose that because of the contracts that you have with agency labor, you want to allocate 14% of the forecast revenue of financial services in Europe. And the forecast for the next 6 months is $14.7 million. So you allocate based on the contracts that you have 14%. Then you say we want to allocate 18% of this revenue forecast to offshore resources, and this represents $2.6 million. And the rest, 68% of the revenue forecast will be for onshore resources in EMEA. And onshore resources can be divided into internal workforce and contingent workforce. So 68% of the revenue forecast is about $10 million. So financial services are expensive, so the rate per day for these services, let's assume that is $10,000 per day. So if you divide the $10 million that you want to deliver by the daily rate, you will see that you will need to bill 1,000 days. Then Andrei Fusiek developed a sophisticated formula to compute the productivity of the onshore resources at financial services in EMEA. And basically, this is like a weighted average of the productivity of the internal workforce and the productivity of contingent workforce, minus a risk factor that consider unexpected delays in the delivery of projects. So based on this formula, and given the parameters that Andre or the planner provides for these service offerings, the productivity of onshore resources is 64%. So if you divide the billable days by the productivity, you will see that you will need to work 1,562 days. So now let's assume that in 6 months, a person can work 130 days. So if you divide the working days by the 130 days, you will see that you will need 12.02 FTE for onshore resources at financial services at EMEA. So based on history, you might know that 10% of these labor requirements are represented by solution architects. So oh no, before I do that, the planner will say that the total labor requirements of onshore needs to be, the contingent workforce needs to be 20%. So 20% of 12 FTE is 2.4 FTE, and this will be the contingent workforce that you will hire. And the rest, 9.62, will be internal workforce. And now for the internal workforce, you know that 10% represent the solution architects. So about 1 FTE will be solution architect. Then you know that the business consultants is about 3%. So you will need about 0.3 of a business consultant. So a business consultant will be working on financial services at EMEA 30% of her or his time. And the rest, 4.4 FTE, will be technical engineers or technical consultants working on delivering these services. And to compute the number of project managers, you consider that the manager manage an account of $3.5 million. So if you divide the forecast revenue, $14.7 million, by the account size, 3.5, you will get 4.2 project managers. So now the planner, it will compare the FTE requirements with the people available. And then the planner will compute gaps and will compute surplus. And if the gaps and surplus are unacceptable, basically the planner will start making changes in the percentage of contingent workforce to be allocated, or the percentage of offshore or percentage of labor agency. So you can see that there are several limitations in this manual approach. So for example, this manual approach misses the opportunity to maximize total gross margins for all market offerings. So you don't operate in a coordinated way. And also misses the opportunity to increase resource utilization by training and reskilling. And by manually adjusting revenue allocation parameters and labor sourcing parameters in a trial and error fashion takes a lot of time. So that's why when we start discussing with Andrei Fosiek about the possibility of using mathematical optimization, he was very excited to do that. So now what I'm going to do is to make Professor Haitao presenter, and he will continue this presentation.
Now let's take a look at how to formally define labor strategy optimization. LSO stands for a prescriptive optimization methodology and tool at the strategic level to optimize the staffing decisions for a professional service organization. It provides decision support for the following 4 dimensions of decisions. That includes capacity, capability, location, and flexibility. Capacity refers to the headcounts of FTE that will be needed. Capability refers to the types of mix of skills and roles of those FTE. Location refers to where to source the labor, that is, whether offshore or onshore. And flexibility refers to the mix of internal and external workforce, and also cross-training opportunities. IRSO is very much a data-driven decision support approach. These data as inputs that include the target revenue of each market offering, firm-specific service transformation process, which we will see in a minute, and firm-specific cost structure of labor, and the firm's available capacity of its current workforce, cross-training policy and rules, and risk assessment and management information. IRSO provides the following 3 types of decision support. The first is it will prescribe the optimal amount of each resource needed to meet the targeted revenue and the amount of resource for cross-training, and also identify some potential gaps in capacity and capability. Now let me dig into some key components of developing the IRSO model that includes modeling the bill of labor, cross-training, and how we handle the supply side risk and uncertainty. The term bill of labor is very much analogous to the well-known bill of materials in the manufacturing setting. It describes the firm's specific service transformation process and service delivery. It takes a hierarchy of labor resources as inputs and have the generated revenues as outputs. It includes the dependent demand of labor resources as the building blocks. Now, here are the key data needed for describing the bill of labor structure. We've already seen most of these data when panel went through the spreadsheet manual approach. Here we introduce some notation. We use tau to represent the discounted internal rate, that is the productivity of an internal workforce. Eta represents the number of working days in the planning horizon. Lambda I refers to the risk of offshore resource operation. And we use mu to represent the commitment rate of FTE as the percentage of FTE time that are billable divided by the total number of hours worked. We use phi ij to describe the amount of effort, that is the efficiency of training needed to transform FTE with row I to row J. Now we introduce a very important concept for describing bill of labor, that is the multiplier. We use the notation Hij to describe the demand dependency amount between the labor with row I to labor with row J. Now the simplest form of multiplier is for describing the revenue and FTE allocation. So here the multiplier is simply a scalar of 1. Now when we want to describe the revenue generated by one internal FTE, the multiplier becomes tau multiply, recall tau is the productivity per FTE, tau multiplied by eta, that's the number of working days in the planning horizon. Now for offshore FTE, we need to factor in the risk factor of offshore operation, lambda. To compute the effective FTE hours, considering the efficiency of commitment rate, so here mu I becomes the form of multiplier. And to describe the efficiency of training, we use 1 minus phi ij as the multiplier. Now let's put this multiplier into context. So in the first example, we're showing the split of target revenue into offshore and the third-party partner. So here you can see the multiplier is simply a scalar of 1. Now similarly, to decompose the total FTE into FTE with different rows, we only need multiplier of scalar 1. And to model FTE's productivity, the multiplier is tau multiplied by eta. For offshore FTE, we factor in the offshore risk lambda. To transform the FTE headcounts into the effective FTE, we use the multiplier being mu. And finally, for modeling workforce transformation, the multiplier is 1 minus phi. Now let's take a look at a concrete example of bill of labor. In this bill of labor structure, notice that on top is the output of service delivery, that is forecasted target revenue. And the bottom of the structure are the inputs. These are the FTE headcounts. So different from the spreadsheet approach panel described earlier, when we model the bill of labor structure, it's more intuitive to go from bottom to top. That is from the input to output for service delivery. And here you can see the role of those multiplier. For example, to deliver the forecasted revenue, the multiplier 1 is needed. So the total revenue is simply the summation of onshore revenue plus third-party partner allocation and offshore revenue. And we can see for nodes in between, its total demand is the summation of its predecessor demand multiplied by the multiplier and add all the predecessors up. And at the bottom, it shows the workforce transformation. So here is the place we have a little bit more complexity. So here for the FTE headcounts, we need to make sure that the demand of FTE satisfy a relationship that involves its current inventory, the amount of FTE transformed into a specific role, and the amount of FTE transformed out of that role, and plus any potential idleness of that role. So we will see later on in our model formulation, we'll make sure that we build the right form of constraints to model the structure of the bill of labor. Now let's take a look at how we model cross-training. So here we are showing an example of the possible cross-training between two market offerings and among 4 different roles. And as you can see, these rules and policies can be highly firm dependent. Each firm may have their different role so that they can customize the possible training across market offerings and roles. So the percentage number here indicates the phi ij representing the amount of effort for that pair of cross-training. Unlike the typical bill of materials in the manufacturing setting, in bill of labor for service delivery, decision maker may encounter significant amount of uncertainty, mainly because of the high degree of customization and the underlying learning effect involved in service projects and delivery. So one way we utilize to model this uncertainty is to treat some of the input parameters, for example, those parameters involved in the multipliers as stochastic random parameters. For example, the commitment rate of mu of FTE can be uncertain. The offshore risk factor can also be uncertain. Now let me go through the deterministic mixed integer linear model formulation. I'm not going to go through all the notations, but I would like to draw your attention to the following pieces. First, we would like to differentiate some of the nodes, that is the type of resources in the bill of labor. We differentiate the set of market offerings, which are usually on top of the bill of labor structure, which is indeed the outputs of service delivery. And VI stands for the set of internal regular workforce, which is typically on the bottom as inputs of the service delivery process. And the set of nodes of VO stands for the set of outsourced resource and labor. And all other nodes, including those nodes in the middle of the bill of labor structure. And also pay attention to this HIJ, that's the multiplier we explained earlier. So in our formulation, we're going to use HIJ in this generic form to describe the demand dependency. But recall that HIJ may involve, these parameters such as mu and lambda and other parameters as special case. The decision variables of our model, very important one is the definition of Xi as the amount of resource I in the bill of labor structure that's needed. So here, Xi is defined in a generic way. Depending on the meaning of node I in the bill of labor, Xi may carry different meaning. For example, when I represent a market offering node, Xi represents the breakdown of revenue of that target revenue. When I represent an internal workforce, Xi refers to the FTE headcounts. And we use Yij to describe the amount of cross-training from row I to row J for any pair of eligible cross-training defined by T. Again, T can be firm-specific. And we use some additional binary decision variables like eta and eta to track the status whether an FTE being idle or not, and epsilon I to track whether the internal workforce I can be positive or not. And phi ij indicates whether a cross-training happened between row I and row J. Now, these auxiliary binary decision variables are needed to model some rules the company may have concerning cross-training. The objective maximizes the gross profit, the total profit of the firm as the total revenue, subtract 4 cost components. The first cost component is the cost outsourced to third-party partners. The second cost component is the cost of regular internal workforce. The third cost component is the cost for cross-training. And the third one is the cost for an internal workforce being idle. Constraint 3 decompose the target revenue for a market offering into different sources. And constraint 4 computes the demand of resource with row J as the summation of its predecessor. Notice the notation we use here. Ij represents a pair of nodes in the bill of labor where I is the predecessor of J. So we consider the demand of J's predecessor Xi multiply by the multiplier between I and J and sum over or J's predecessor. Constraint 5 computes the headcounts of FTE as inputs to the service delivery process. You can see a specific row's headcounts equals its current available capacity, subtract any cross-training that's being cross-trained from row I to other rows, plus cross-training from other rows into row I, and subtract any idleness. Constraints 6 and 7 are the so-called big M formulation to track whether a resource I is being idle and whether a cross-training happens. Constraint 8 models a business rule that a typical firm may have to restrict cross-training and idle workforce. So you can have idle resource row being idle and also being trained, cross-trained at the same time. To deal with uncertainty, we employ a two-stage stochastic programming model. So we consider a set of random parameters, for example, the commitment rate of a resource, FTE, and the risk of offshore operations. We use W tilde to represent the set of all the random parameters and assume that this set of parameters follow a joint discrete probability distribution, and with P omega being the probability for scenario omega to happen. A key in building a two-stage stochastic programming model is to identify the so-called first-stage decision variables and the second-stage decision variables. First-stage decision variables is also known as here and now decision. These are the decisions that decision maker needs to make right now before the uncertainty is resolved. So in our LSO setting, we identify the first stage decision variable as the target revenue allocated into different market offering. And this decision has to be made before the actual service delivery process happens. And all the other decision variables, as we showed in the deterministic model, are identified as the second stage decision variables, which we may call recourse decision variable. As you can see, these decision variables are defined to be associated with each random scenario. So they prescribe the decision and to inform the decision maker what to react when that certain scenario happens. So in the two-stage SP model, the objective function becomes maximizing the total expected gross margin as the total revenue subtract the expected total cost. So you can see the expected total cost is computed as the weighted average of the total cost with the weights being the probability of each random scenario. Let's pay attention to the first constraint in the two-stage stochastic programming formulation. First constraints only involve the first stage decision variable without the random parameter. So here we allocate the target revenue of a market offering into different sources. And all the other constraints that are similar to those in the deterministic formulation are defined to be associated with a particular random scenario. Now let me present a use case we came up with using real-world data. The data has been masked to protect the proprietary information, but the use case has all the features of LSO to demonstrate the behavior of the solution and its advantage comparing with the spreadsheet approach. In this case study, we consider 7 market offerings with their forecasted target revenue to be met. And here is the bill of labor structure of one market offering with the multiplier shown. And we have data on the capacity of the internal workforce of the company by market offering, by role and location. And the similarity coefficient for cross-training, that is our phi ij. And here I want to point out that these phi ij values can be obtained by some predictive analytics using either the traditional statistic predictive methods or some more recent technique such as machine learning. But these numbers can be highly firm dependent as well. We compare our optimized LSO solution with the manual spreadsheet approach and the restricted optimization approach. In the spreadsheet approach, as we saw earlier, much of the decision relies on a pre-specified percentage allocation rules and subjective judgment. Now, in the restricted LSO approach, we allow certain flexibility of those allocation rules, but still fix the percentage of third-party partner allocation. So as you can see, LSO solution achieves significantly higher gross margin comparing over the other two approach. And you can also see the prescribed optimal staffing decisions are also quite different from the other two approach. We have performed a significant amount of computational experiment to obtain further managerial insights. So if you are interested, feel free to check out our working paper that includes a full set of computational results. Here I select a few we believe very interesting ones to show you. So the type of analysis we performed are essentially sensitivity analysis. The first result I want to show you is the sensitivity analysis between the bill rate, that is the productivity of internal workforce, and the financial metrics. As you can see, as the internal workforce becomes more productive, the gross margin increases as the blue bar increases, and the total cost of service delivery decreases. Total cost of service delivery goes down. Well, what is interesting here is that, as you can see, the benefit of having a higher productivity actually goes down, which indicates a sort of diminishing return of the productivity of internal workforce. And it also shows the optimal labor mix as the productivity goes down. As the productivity goes up, the optimal labor mix will prescribe more utilization of regular workforce and use less contingent workforce. And as internal workforce becomes more productive, it is optimal to have more cross-training to increase the utilization of internal workforce. And this is the case in both onshore and offshore. In this graph, we show the relationship between the commitment rate of contingent workforce versus the total FTE of labor mix. So as you can see, as the commitment rate of contingent workforce goes up, initially, contingent workforce becomes more attractive comparing with regular workforce. That's why you see the utilization of contingent workforce goes up initially. Up to the point, in this case, about 30%. Then, as the commitment rate of contingent workforce keep going up, the utilization of CTW actually goes down, because now CTW becomes so effective that less will be needed to meet the same amount of demand. Now, what I want to emphasize here is that without a concrete optimization approach, none of these insights will be intuitive using a manual approach. So now let's take a look at the effect of offshore risk. So as the offshore risk goes up, the gross margin goes down, and the total cost of service delivery goes up. And it also prescribed the optimal mix between onshore labor and offshore labor. As offshore operation becomes more risky, it is optimal to utilize less offshore labor, but more onshore allocation. Now, Pano will share with you the lessons learned and best practices.
So the first lesson is that mathematical modeling is really an iterative process. So basically, what happened in most of cases, and what happened in these cases, somebody identifies an opportunity to improve a business operation, and so you, as a modeler, will start talking with the business people that eventually will be your end user. And you need to get an understanding of the business situation in such a way that you can define business requirements. And it's very important to, when you are defining the business requirement, to have a problem statement. What is the problem that you are going to solve with your optimization technology? And this problem statement should reflect the optimization model that you are planning to build. So you will define the objectives that you want to optimize. You want to define the type of decisions that the model will recommend, and you want to define the type of constraint and business rules that determines or constrain your decisions. So the first thing that you do is you start writing your equations for the optimization model, and then basically you build a model, and then that model will have parameters or input data. So that will be the data requirements for this particular problem. And then you don't present the mathematical model to the business people. They don't like to see the math. So what they like to see is results. So you build a prototype, a software prototype, that you can show reports and you can do what if scenario. So basically, with this software prototype, you want to build confidence from your potential user and the business partner that you have, that the model really is behaving in the way that they can trust it. So when you start running this model with the real data and showing reports and all of that, you need to ask the user if or the decision maker if the recommendations of the model are implementable. So if the decision makers say no, they are not implementable because they are violating this rule, or because we have another objective that we have not considered, etc. So basically, you need to go back and then review your business requirements, certain constraints or decision in your model, etc. And you continue with this process until the decision maker say yes, I can implement that decision. Then you transfer as a beta version of your prototype to your users for final debugging and stabilization of the prototype. And then what you need to do is to transfer the software prototype to the IT organization for long-term support. This is the lesson number 2, that if you don't transfer your prototype solution to an IT organization, then the probability that your application will die is extremely high. Why? What is happening is that the systems like SAP, Oracle, Salesforce, or whatever system is generating data for your application is going to be upgraded and evolved. And if your prototype solution has been not transferred into IT, your application won't be part of the IT development roadmaps. So at some point, your application won't receive the data required, and the user won't be able to use the tool. And at that time, your application just die. So it's very critical for the long-term survival of any optimization application that you develop, that you transfer it to IT. And lesson number 3 is evangelize mathematical optimization at your company. This particular application that Haitao and I developed basically came from that. At HP Labs, we used to talk, create tech fairs and seminars and all of that. And we start talking with the workforce planner of HP Consulting and Integration. And they start showing us the challenges that they have. And that's how this project started. Because what is happening is, I bet you that in your company, you have a lot of maximization operational efficiency problems related to business function and business units. So educate your business people and top executives about the money that they are leaving on the table by not using mathematical optimization. And as I mentioned, organize seminars, tech fairs, advertise your success, and show how mathematical programming can improve the operational efficiency of your organization.